Okay, so I apologize for the audio sync issue on the last one. I think the audio was probably moving a little bit fast. I've forgotten it's an issue that we have with USB headset microphones and these new computers that we got just last year. So don't know what it is, but there you go. I'm now using the built-in microphone in the computer, and that seems to at least keep the sound synced up, even if it's not the best sound quality. So apologies for that, but let's continue. So here we are with problem 4 on this review sheet. We have a truck driving uphill, the driver using just enough gas to keep a constant speed. And this is where our little forces, what we know about forces and remembering it comes in really important. So the driver is using just enough gas to keep constant speed. Constant speed means acceleration is 0. Or 0 if you draw it correctly. There we go. Okay, so here is here's our free body diagram for the truck. Gravity always down. Gravity down. The end of gravity. Okay. Normal force has to be perpendicular to the surface. There is no other option. Okay, so normal force must be going that way. Now, and it's going at an angle of theta with respect to the vertical. Okay, now here's the tricky part. What other forces act on this guy? Tension? Is there any tension? No, because there's no string or cable or rope connecting this guy to anything else, obviously. So the last force we could possibly have that we know of right now is friction. So could friction be acting? Well, sure. The tires are on the ground. Friction between the tires and the ground. It makes sense. Which direction is it going to act? Now, you might think, oh, friction is always going to act opposite the direction you're going. That's not quite true. Friction acts opposite the direction of slip. It's opposite the direction that you would want to slip, or that your surfaces would try to slip over each other. Okay, so it doesn't necessarily have to be against the direction you're moving. For example, and here we go. In this case, what's happening with the tires? So let's say there was no friction, and the tires. Well, there's a tire. Actually, that's a horrible tire. So let me just draw a close-up of one of the tires of the truck, okay? That's this guy. If there's no friction and the guy hits the gas, the tires spin this way, okay? And they just go that way, and they will slip over the ground. Notice the direction the tires are going as they go over the ground. They're going this way, which means the tires want to slip downhill. So friction acts on the tires to stop them slipping, which means friction pushes you uphill. Okay, so friction does, in fact, go this way. Here's another way to think of it. Suppose, suppose we had no friction. Suppose there was ice. So this friction is gone. The wheels are made of Teflon, and it's ice coated with oil, and pancake grease and whatever else. I don't know why I said pancake grease. Oh, anyway, so there's no friction whatsoever. Well, you couldn't go uphill, right? If you happen to be going uphill and then you hit a patch of ice, then you would start sliding back down, right? And without this friction, let me just erase that out. Without this friction vector here, that doesn't happen. So, I mean, you do accelerate downhill. So, in order to not accelerate downhill, in order to have an acceleration of 0, we have to have friction going uphill. And look, I mean, if acceleration is 0, you have to have all your force vectors have to sum up to 0. There's no possible way these can add up to 0 unless mass is 0. And if mass is 0, then, what's your point, right? So it has to go that way, the Sherlock Holmes theory. We've eliminated all the other possibilities, but there has to be a force uphill, so what's left is friction. That's got to be it. Okay, let's see if we can get over to 5. Okay, same truck, I guess, now driving through a bank turn to the left at a constant elevation, and he's driving faster than the recommended speed. So let's remember the recommended speed. What I mean by that is the speed that they post as, here's what we recommend you take this exit at, or this turn at. And that corresponds to the case where there's no friction. Okay? So if there was no friction, you'd be going at the recommended speed and you'd be fine. So let's first of all say this guy's in a bank turn to the left. So he must be turning towards the center of his circle, right? So this is the direction. Left is the direction he's accelerating. Okay? So he's accelerating horizontally to the left, constant elevation. So he's accelerating horizontally to the left. And if you need to see that, pretend this is a top view. Here's the truck, okay? And he must be accelerating towards the center of the circle since he's going around this way, right? Okay? So he he needs to accelerate to the left. What forces act on the truck? First we have gravity, always have gravity. We have normal, which is always perpendicular to the surface, no other options, okay? And then what's left? No tension, so friction, got to be friction. Now he's going faster than the recommended speed. Let's think about if he were going too fast, would he tend to slide off the road to the inside or the outside? If you think about it a minute, think if this road was covered in ice, he'd be sliding off to the outside, right? He'd be doing that if he was going too fast and had no friction. So what friction is going to do is friction is going to try to keep him going inward. So friction has to pull this way on him, okay, and get him moving more inward, because this dotted line going out, that corresponds to him in this picture, which is looking at him from behind. That corresponds to him going do 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 and flying off. Okay. Another way to see it is that when you have no friction, you can go this certain speed. If you go with the recommended speed, if you're going faster than the recommended speed, okay, so if you're going faster than the recommended speed, so your v increases, then your a must also increase. So you have to have more acceleration, which means that friction has to provide even more force this way in order to get you the acceleration inward. Okay. And last truck question. Actually, not the last truck question, but almost the last truck question. The truck is driving on a flat, level, straight road, constant speed, and we're going to include air drag for this problem. Okay. So forces we got, of course, mg, and the normal force. Okay. We have air drag. Now, should be pretty obvious. If he's going this way to the right through the air drag has to be a force acting to the left. Okay, so it's FA, I'll call it, for air drag. And what's left?